when we have a frequency distribution, we can also consider it a type of probability distribution. How would that work? Well, let's just say that I have people come into the store and they're going to buy coffee. And how many people buy the coffee? Well, let's say that it's a Friday and I have different possibilities. So I might have, let's say 2 people buy coffee. Maybe I'll have 4 people or 6 people or 8 people. And so I have these possibilities. These are the numbers of people that are buying the coffee. And then I say, how often does that happen? What is the frequency? And let's just say that this was 6, 14, 18, and 2. Okay, that's a frequency distribution. But I want to change this. I want to make it into a probability distribution. How can I do that?
You just take all the numbers for the frequency and add them up and then divide whichever the single ones by the total.
That's correct. What do I call that? What's the name for that thing?
Relative frequency.
Relative frequency, okay? Relative frequency is the same thing as observed probability, okay? So this is frequency, but if I'm going to have relative frequency, I can also consider that to be an observed probability. How many total people do I have in my set here? What did you say?
40.
40. I have 40 total people. So I want those numbers. I want to know my relative frequencies right now. So you might want to use your calculator unless you can do this in your head. If you can, that's fine. So what's my first number?
15%.
Okay, and I'm going to express this as a decimal number. Next one.
135.
All right. Next.
0.45.
And last.
0.05.
All right. These are my observed probabilities. When I'm looking at these observed probabilities, I'm looking at my measurement. The measurement is the number of people buying coffee. You need to make sure you understand the difference here. The measurement is not the probability. The measurement is the numbers of people buying the coffee. And then I have them in these different probabilities because they happened a certain number of times. This then is creating for me a probability distribution of my data. This is my data set, the 2, the 4, the 6, and the 8, how many people buy the coffee. But then this is how frequently that happens. So if I wanted to, I could do some kind of a histogram with this, right? 2, 4, 6, and 8. And I'd have like 50% up here, 25% here, 15, 35, 45, and 5. So what we're doing here is we're describing the behavior of my data. How often does the data occur? The measurement is what's on the horizontal here. But this thing here is a description of how often it occurs. So then I now have the probability distribution of my measurements. And this has a specific name. It's called a discrete probability distribution, because I have separate numbers here, 2, 4, 6, 8. Those are distinct numbers. They jump 2 to 4, 4 to 6. These are discrete numbers. So it's a discrete probability distribution. Now, if I were to ask a question, how do I find my unusual values? What would you say? Dalton, can you tell me what I have to say for unusual values in this situation?
Anything that's under 5%, typically. So in this case, we have your 8 value, which is at exactly 5%.
Okay, so if I'm looking at this and I say, what is an unusual thing to happen? It would be kind of unusual for me to have 8 people buying coffee, because that only happens 5% of the time. Did I use my mean and standard deviation? I did not. Do I need to? No, I don't. I already have the probabilities. I don't have to wonder what the probabilities are. I know what the probabilities are because they're in my little table right there. So when I'm looking for my unusual values, or for what to expect, right? That comes directly from the probability. I don't have to do any other fancy calculation. I just look at the numbers, the probability numbers. However, it is possible for me to actually come up with the mean of my data set based on this information. And that can be useful, right? Because the mean is one measurement of where the center of the data would be. So I need to be able to use this to make it happen. Now, what we're looking at here is that the number 2 occurs 6 times. The number 4 occurs 14 times. So I could take 2 and write it a bunch of times, 4 and write it a bunch of times, add them together, and then divide by the total number of numbers, which would be 40. But there's a shortcut way to do that. Instead of me going through that entire process, I have this formula. The mean, which I use this letter mu, the Greek letter mu is going to stand for the mean, is equal to this. Now, what is represented by the letter X? The letter X is representing of my data values. That is this first column. That's X. X is the thing that I'm measuring, which is the number of people buying coffee. What is the probability of X? That would be this column. The chance of X happening. So notice what I'm going to do in this situation is I'm going to take each of my data values and multiply that data value times its probability. After I do that, I'm going to add that total, and that will give me the mean of my data. Okay? So let's make that happen. I'm going to rewrite this now. 2, 4, 6, and 8. And I'm going to have 0.15, 0.35, 0.45, 0.05. These are my data values. These are each of my probabilities. I'm going to multiply those. Remember that the X in parenthesis is just a label telling me which one it is. I don't actually put the number into the parentheses in that sense. It's just a label telling me which one it is. So I'm going to take each data value times its probability and add those up. And so yes, I want you to do that right now. I want you to take each of these numbers and I want you to multiply each one times its probability. And I want you to tell me what that total is. Jaren, you got numbers for me?
Yes.
Okay.
0.3, 1.4, 2.7, 0.4.
And if we add them up? 4.8. Okay. That number is the mean. This is the average number of people that come into the store to buy coffee. Is that reasonable? Well, certainly it better be. Looks like 4.8 is around in the middle here of my numbers. And so yes, this is reasonable. It is the mean. Right? So then, what this allows you to do is that if you have any collection of data which has frequencies like this, you can then make it into a probability distribution and find the average. So if you want to know the average of whatever set of data, and all you have is the frequency distribution, then you can make this happen. Now, it is true that we can also find the standard deviation. But I just want to emphasize to you that the empirical rule does not asterisk apply. There is no reason for us to try to use the standard deviation in order to predict unusual values. Because we already know the probabilities, it doesn't make sense for us to say, well, how can I figure out where the unusual values are? I already know that answer. However, just for completeness, we do want to be able to find the standard deviation of this kind of situation. So here's the formula for the standard deviation of a discrete probability distribution. It is the square root of this. Now, these formulas are certainly in your textbook. They are in your list of important formulas, which is in the resources section. They are on the PowerPoint presentations. So yeah, they're all there. So if I look at this data set and I say, I want to know what is the standard deviation for these data values, 2, 4, 6, and 8. What I'm going to do is I'm going to start by squaring the x values and then multiplying those times the probability. You have to be careful that you're choosing the correct columns here. I square the x values and take those times the next column, which is probability. I don't use the third column. Generally, I take the square of the first times the second. So, in the interest of time, I'll just do this up here. So this is 0.6, 5.6, 16.2, and 3.2. This is x squared multiplied by each of the probability numbers. And if I add that together, I get 25.6. That's my total. So once I get that, that number goes into the formula, but it's not the final answer. I'm going to take 25.6 minus 4.8 squared, and then that result, I take the square root. And that will give me my standard deviation. So, turns out to be 1.6. Once again, if we ask the question, is that reasonable? Well, if my mean's 4.8, that's in the middle. If I go 1.6 on either side of that, then that's where my data is, and I can think about 2 or 3 standard deviations away, but that's not really an issue here. The standard deviation for this situation might be convenient, but it's not really meaningful because it's not really telling us about the unusual values. The probabilities by themselves are telling us about unusual values, so we don't need to go through the empirical rule for this. All right. Now, one thing that's really important, though, when we talk about the mean, is that this is also a way to understand what is likely to happen in a specific context. And of course, I forgot my eraser. But let's say that I'm going to run an ice cream business. And I want to make profit. But there are certain things that are going to happen in my ice cream business. Let's just say that I happen to get a resort location. I guess I have to move this over. If I get a resort location, then I'm going to make $5,000 in my ice cream business. If I'm not able to get a resort location, then maybe I'll be able to get a downtown location. And if I have a downtown location, then let's say I can make $2,000. But let's say I can't get either a resort or a downtown, so I have to get a kiosk. And if I get a kiosk, I'm only gonna be making $500. And this is going to be, I don't know, let's just say these are monthly totals, okay? Now, how much am I going to have in terms of how likely are these things to happen? So I'm like, okay, I've got my business. How likely is it that I can get a resort location? Well, let's just say that's a 10% chance. There's not much chance of that happening. How about downtown? Well, let's say that's like a 30% chance. Well, what about that kiosk? Well, that's actually the most likely thing to happen, 60%. So here are my profit numbers. Here's my X. This is the probability of X happening. What will be the meaning of the average or the mean in this situation? This is something called the expected value, which is a bad phrase. It doesn't mean what you think it means. The expected value in this situation is actually the long-term average. It doesn't mean that I know what's going to happen. It says if this thing happens over and over again, what would be my long-term average? So let's do this multiplying. 5,000 times 10%, 2,000 times 30%, 600, 500 times 60%, 300. I add these together, I get $1,400. Now, am I actually making $1,400? The answer is no. I either make 500, 2,000, or 5,000. But if I have over a long term where these things are likely to happen with these probabilities, then I would come up with an average of $1,400. So this is going to tell me not what happens in each situation, but it tells me over the long run, what is the average thing that's going to come out. Now, would it seem reasonable that I would invest in this business? That I would want to make this happen? Well, $500 is not nothing, right? And $1,400 is certainly over the long term what I would get. I can't expect to be at a resort all the time, but it is a profitable thing. And so I would have to keep in mind, it's not 500, it's not 5,000, it's going to be in the middle eventually over time. This is how insurance works. What are the chances of me dying anytime soon? Somebody knows. Somebody has it figured out. These are the chances that this person's going to die or that person's going to die. And so life insurance says, hey, tell you what, we'll give you money, and if you die, we'll give you a couple of $100,000. But the chance is you're not going to die, and we're just going to take your money for a long time. And then you die, and we give you hundreds of thousands of dollars. But most people don't die, and so then they're able to make a profit because they can take my money, and most people don't die. If they did, then they would lose their money, but they don't. Same thing is true with car insurance. Is it true that if you get good grades, you can go to your insurance company, show them your good grades, and they'll give you a break on your insurance? Yes, it is. Why would that be true?
For some reason, they assume that better students are better drivers.
For some reason, they assume that if you get good grades, you're not going to have as many accidents. And you know what? That has to be true, or else they wouldn't do it, right? There would be no reason for the insurance company to just say, hey, let's just pick people with good grades and see what happens. They're actually doing it because it works. I mean, you wouldn't think that they're just out to do things for no reason. There's a program that my insurance company has. They can put a little GPS into my engine block and know where my car is at all times and how fast it's going. And they will give me a break on the insurance if I put that thing into my car. Because then they'll be able to find out if I'm a good driver or not. And they will be able to say, hey, you know what? You go over the speed limit all the time. You accelerate too fast at every stoplight. You slam on your brakes all the time. So therefore, you're not a good driver. We're going to raise your insurance. They know that works, and so they are willing to do that. I'm not willing to do that, so it didn't work for me. It used to be that health insurance was the same way. That we would say to people, you know, you're more likely to get sick, and so your health insurance will cost more. Or we'll take all the money from the healthy people, and then we'll use that. But as a culture, we decided that would not be a good idea. We decided that we're going to do something else instead of health insurance that way. Because we say that everybody should get treated no matter how likely they are to get sick. Everybody should go to the hospital and be able to get treated for their sickness. Shouldn't matter whether they were likely to or not. They just go and they get treatment. So therefore, someone else has to pay for that, and it has to be healthy people. Sick people are not going to pay for their sickness because they're sick. So the healthy people have to pay for the sick ones. So you have to decide who's going to make that happen. The government, your employer, a combination of them, the hospital itself, or something. And for a long time, the hospitals have been raising their prices, and then they would be able to raise their prices because the healthy people will pay for those things, and the sick people can't. So the sick people, they don't pay their bills because they're sick, and the healthy people, they do pay their bills. And so then you've got to raise the prices for the healthy people because the sick people can't pay their bills. So somebody's got to do it. Somebody's got to pay the bill. And we say that if you're sick, you shouldn't have to pay your bill. If you're too sick, you just go and you get treatment, but you can't pay because you're sick. So then it's just a matter of who's going to make that happen. So all this stuff about single payer and Medicare for all and all that other stuff, it's just deciding who's going to make those decisions. Because we've decided as a culture, you should always be able to go to the hospital and get treatment. So that's not this anymore, okay, because it's not how that works. Okay, so this is the idea of expected value. All of insurance works this way. This is, again, how Google and Amazon do all their stuff. What are the chances that you're going to spend this much money? And how can we get you into a category where you're more likely to spend money? That's what they want. Now, then there's another situation where this type of thing happens when we're talking about things like a coin flip or a yes or no answer. These are what we call binomial. Binomial means there's only two things that can happen. Yes or no, heads or tails. And so then we're going to define some things, and these are in your textbook and in PowerPoints. But we need to have n X, and P. Those are the three numbers we're going to use. N is going to be the number of observations. X is going to be the number of successes. We put that in quotation marks. And then this is small letter p, and it's called the general probability. So let's say we're talking about how many people watch the Super Bowl. Okay? We're going to ask, let's say, 30 people. X would be the number of successes, and so it could be any number starting with 0 and going up to 30. Could be that everybody of the 30 watched it, or no one. Could be. And then P is the general probability. It is not X over N. It is not the relative frequency. It is not the observed probability. The general probability has to be given to us outside of our observations. Someone has to tell us what that number is. So let's just guess something like 40%. So then we say, all right, this happens. People watch the Super Bowl. I have a collection of 30 people, and I'm going to ask them, did you watch it or did you not? Now, it would seem that there would be the possibility that nobody did. It's possible. It's possible that everybody did. Possible. But then the question we're going to ask is, if I randomly choose people out of this situation where the probability is 40%, what are the probabilities of the different results? What is the probability of X? Now, if we did a tree diagram for this, then every yes would be 0.40 and every no would be 0.60. And then we'd have yes and no, yes and no. Every person would create an additional set of yes or no possibilities. We talked about this earlier, and we figured out you multiply the probabilities as you go. So then if everybody says yes, that would be 0.40 to the 30th power. Well, it's a number, but what we actually want to figure out, though, is not just for everyone to say yes or everyone to say no. We want things like, what about if 13 people say yes? How would we figure out that possibility? So I'm not going to make a tree diagram with 30 different levels all the way out here. That would be too much. But there's a nice formula that we can use that will tell us how this works. So I'll put it up here. For the binomial probability, the probability of X is equal to NCX times P to the X power multiplied by 1 minus P to the N minus X power. So this is a formula that we can use to figure out binomial probabilities. We talked about NCX previously. It's the number of combinations. So this is taking that big tree diagram and it's adding all the different ways to make it happen. It's adding all those things together. And then P to the X, that's just how many people say yes. And 1 minus p to the n minus x, that's how many people say no. So this all goes back to the tree diagram, but it's a formula that lets us figure stuff out without actually making that huge diagram. So let's figure out what would be the probability of having, let's say, 14 people say yes out of the 30. So this is, again, just a label, probability of 14. So this would be 30 C14 times 0.4 to the 14th power, and then 0.6. What's 30 minus 14? 16. So we would have that number right there. Now, as it turns out, we could go through and use our calculator to multiply all these numbers together and make this happen. But if you've got a spreadsheet or some software or the web, you can actually just find out what this is. So I put in 14 successes out of 30 trials. My general probability is 0.40, and I get a number. This would be 0.1101. So I got all these people, 30 people, and I say to them, hey, did you watch the Super Bowl? 14 people say yes. And I'm like, all right, that could happen. It's only 11% about it happening, but yeah, it could happen. Now, technology being the wonderful thing that it is, we can make this stuff happen pretty quickly on various websites and so on. And I happen to have one available, the binomial distribution applet. So I've got n is 30, p is 0.4, and x is 14. There's my number. What's nice about this is that it also shows me a graph. So here is a graph of all of the different things that can happen, all the way from 0 up to 30. And it shows me this graph of what the probabilities are for these different things. So 14, 10%, more or less, that tells me something. What you might also notice is that I can look at this at the 5% level, and I can say any of these things that are less than 5%, I would consider those to be unusual events. So let's just pick one here. 7. The probability of getting 7 people to say yes is less than 5%. And notice it goes down as you go out from the middle. So 7 or fewer people, if I have a general probability of 40%, and I say, hey, who watched the Super Bowl? I'd be surprised if it was 7 or less. 8, well, that's just about 5%. So yeah, maybe 8 would be a surprise too. How about on the other end? 16. 16 people out of the 30. If it's only at 0.4, then 16 would be a surprise, as would 17, 18, and the rest. The highest one here is at 12. So what I'm looking at here then is if I have a general probability that's given to me and I do something a lot of times and I assume that they're randomly chosen, I know to a certain extent what to expect. Within a certain range of possibilities, I can get my 95% and then my 5% on either side. So then having this kind of information allows me to say, I kind of know what's going to happen. Even though it's randomly experiencing, there's a pattern to it. And so I would be surprised if it's lower or if it's higher. I expect it to be somewhere in the middle. So this, this formula that we have here with the tree diagram is actually going to show us something that we can expect to happen based on a mathematical formula, which is kind of what we want, right, in statistics. All right, now, when we do this, we can also find the mean and the standard deviation in this situation. But it's important for you to know what we're talking about here. We want the mean of X. And we want the standard deviation of X. This is the thing we are measuring. How many people out of the 30 said they watched the Super Bowl? That is our data value. Okay? And these are the easiest formulas in statistics. The mean is just n times p. And the standard deviation is the square root of n times p times 1 minus p. So here, if we say there are 30 people, and the general probability is 0.4, the mean would be 12, which, as it turns out, is also the highest possibility thing. What is that truly saying to me? I get a group of 30 people. I ask them, how many watched the Super Bowl? Okay, I get a number. I say, okay, get out. 30 more people come in. How many of you did it? Oh, okay, get out. 30 more people come in. So I'm doing this 30 over and over again, and I'm getting various X. 10 people, 16 people, 12 people, 19 people. And then I say, what is the average? What is the average number of people that I would expect out of the 30? It would be 12. And then standard deviation, and this website is helpful. It already did it for me. Standard deviation would be 2.7. But this is where, if you just take a look at this graph, you might notice something. And that is that this graph looks kind of bell-shaped. Since this binomial thing can turn out to be bell-shaped, then the empirical rule might work for us here. So this is kind of strange, but it does happen if the standard deviation is greater than 3, then X is bell-shaped. And then the empirical rule applies. Now we're close to that here with 30 people. and 0.40, it's 2.7. But let's just say that we say, now I'm going to go to 100 people. I'm going to ask 100 people, did you watch the Super Bowl? If I have 100 people, I've changed my situation now. If n is equal to 100 and p is equal to 0.4, now the mean is going to be 100 times that, which is 40. And then I say, well, what's the standard deviation? Standard deviation, if I go through the calculation, it's approximately 4.9. So this will allow me to figure out my unusual values. If I take 40 plus 2 times 4.9, that's 49.8. And if I take 40 minus 2 times 4.9, that would be 31.2, I think. Or 30.2. So then this would be my interval from 30.2 to 49.8. This will be what I expect. This would be my 95%. And again, we can go here onto the graph. You know, if we go down here, you can see those low probabilities on either side, and you see how they get put together. So then, when we look at this situation, I say, I walk into a room, I've got 100 people. I don't know, it's some kind of a conference. And I say, okay, general probability is 40%. How many of you watched the Super Bowl? They raise their hands. I would be surprised if it's less than 30 or if it's more than 50. I would pretty much expect it's going to be between 30 and 50. Anything else would be a surprise if my general probability is actually 40. So once again, this is now when I'm asking questions about what I expect to happen. If I have large groups, then I'm able to use my empirical rule to actually get a handle on what I think is going to happen. And if it doesn't happen, then might be a reason. You know, if I'm walking into the baseball fan club and I say to them, hey, how many watched the Super Bowl? Maybe they're not so great for football. And so then they're like, who cares? But if it's, you know, the Ray Nitschke Memorial Fund or something, and it's like, hey, that's really important because we know who Ray Nitschke is and he's a great guy. And, oh, football then. All right, so then maybe it would be more than 50 people out of 100. So these are the processes that we're going to be using based on these mathematical formulas. All right, so there's something else in your textbook which is called the Poisson distribution. And it's also in the homework, I believe, pretty sure, that there's some problems dealing with the Poisson distribution. That distribution is different. It's still a discrete thing, but it's a situation where we don't have a limit to the number of things that could happen. It would be like, how many rocks are going to be in this muddy place? And we say, I want to know how many rocks are larger than 3 inches in diameter. Well, you could find any number, right? But it's not going to be solid rocks because it's muddy. So you're going to have some rocks over here, some rocks over there. So it's things that are distributed within either an area or an amount of time. And then based on that, you say, what am I likely to find? In a small area, how many rocks am I going to find? Certainly they're not all going to be in there, but it might not be zero either. So the Poisson distribution is a way to describe things that happen over a period of time or over a geographical distance or something like that. So it's not quite the same as binomial because you could find any number of rocks, but it is the same kind of idea. Either you find one or you don't. But it's a different situation. Here we're saying I have a certain limited number of people that I'm asking. Where in Poisson, it's like, well, I could find anything. So that's not going to be on the quiz, but it is in the homework, okay? And it's there for your learning so that you can go through it and you can say, okay, I've seen the Poisson distribution. And that's really helpful for things like call centers or restaurants or people out in nature that are looking for birds. They use things like Poisson distribution, but we're not going to really focus on it. All right, hopefully that's good enough for you. And if you have any questions, let me know.